Hi, I'm Hazel, and today I'm going to be presenting my work on Bingus, a program synthesizer for the How to Design Programs curriculum that I worked on with Tobin-Hochstadt. To start off, because we're making a program synthesizer for a particular curriculum, we need to talk about what that curriculum even is. The How to Design Programs curriculum and textbook involves pedagogical subsets of the Racket language, starting off with a very simple language called Beginning Student, and adding higher-order functions with the Intermediate Student language, and lambdas with the Intermediate Student with lambda language. The textbook is written by Felleisen et al., and we used it at Indiana University for the course C211, a course that about half of our freshmen take. HtDP emphasizes reasoning based on this thing called the design recipe, which is a kind of formula that ensures signature and test-driven design. Before we talk about the design recipe, we have to talk about the fundamental building block called the template. The template notes that we have a correspondence between the shape of a data definition and the shape of structural decomposition, or structural recursion, on that data definition. As an example, here we have a structure with three fields to represent a year, month, and a day in a date. Each of them has corresponding signatures, number, string, and number. The template for this is rather simple. It merely extracts every possible field from the struct. Because number, string, and number are simple, we don't have to do any more processing. We can do the same for enumerations of other kinds of simple data. Here we have enumeration of specific strings, red, yellow, and green, to represent a traffic light. Our template is going to tell us that our function needs to take the shape of a conditional, doing something different in each cond. When we get more complicated, such as enumerations of structures or structures of enumerations, especially when we introduce recursion into the mix, this approach is very advantageous. As an example, here we have a tree of dates, which is either a leaf or a node with a tree of dates and a tree of dates on the left and a date in the center. Our template looks significantly more complicated now. We start by noting that we have an enumeration, so we add a conditional that checks each case. In the leaf case, we have nothing to process, so we don't do anything. And in the node case, we have three things to process. Because a tree of dates and a date are not simple, we call the corresponding processing templates. When a student is to do recursion, they can replace the name process tree of dates with something else. And this immediately shows the student how to do structural recursion without thinking about how solutions relate to other solutions. Now we can talk about the design recipe in full. To start off, we have our students write data definitions, which is a description of the data in a comment. We then have a student write a signature and a purpose statement. This is effectively a type, although it is somewhat more permissive, in a comment, and a purpose statement is simply a comment describing what the function should do. Here, we are designing a function called multiply by, which takes a list of numbers and a number, and multiplies everything in that list of numbers by the number. We then write unit tests, or examples, for our function. The How to Design Programs curriculum and the Beginning Student language provides a form called check-expect, which adds integrated unit tests into the language that behave well with the Dr. Racket IDE. Here, we say that multiply by of empty and 3 is constrained to be empty, and so on. Later on, these tests will be automated. We then have the students write the template. We already know what the template looks like, so we can pretty easily gloss over this step. Finally, we have our student fill in the ... dots in the template. In this case, we replace the ... in the empty case with empty, and the ... in the cons case with the multiply by function, where we multiply the first element by n and then cons it on to the rest. Finally, we run our function, and then the Dr. Racket IDE will tell us that all of our tests passed. This is a completely designed function and would get full marks in 211. We now want to determine which one of these things are inputs to the design recipe, and which ones are outputs that the design recipe guarantees to us for free. The data definition, signature and purpose, and unit tests are all constraints on the problem itself. We cannot reasonably ask a computer to make these up for us without not adequately specifying what the problem is meant to be. Effectively, all of this is merely an interpretation of the problem statement that we give students in English. However, the template and testing are completely outputs of the design recipe. The template is entirely determined by step 2, the signature, and testing is merely the result of running the program. The question is what to do about step 5, our function definition, where we fill in all the holes provided by the template. We then create steps 4 to 6 as a closed loop, which is our contribution with Bingus. As an example, we're going to design a function called depth. Depth takes a tree of numbers and computes the maximum depth of that tree. We start off with our data definition, our signature and purpose, and some check expects. Then, we note that our function takes in a single tree as an argument, and that we have some hole that should be in the shape of a number. So how do we get a number? An easy way is to say that 0 is a number. This is a completely valid function definition. However, it does not satisfy our tests, despite satisfying the signature. Therefore, we need to try something else. We can try other things, such as guessing various functions, but instead, let's try to guess the template. The template then introduces this conditional where we check if it's a leaf or a node. In the case of the leaf, we do something, and in the case of the node, we do something else, possibly with recursion. One possible thing we can do is take the max of 2 different numbers. Because the max of 2 different numbers takes the shape of a number, this is a valid option. Finally, we can continue filling in these ... dots. So for the first one, we can fill in 0, and for the second one, we can fill in the design recipe provided inputs, depth of node left, and depth of node right. When we run this, all of our tests pass. We now move to discuss the implementation of the Bingus program synthesizer, and where we got our work from, and how we built on it. To start, Bingus is largely inspired and based on the Myth program synthesizer from this PLDI 15 paper, Type and Example-Directed Program Synthesis by Peter Michael Osera and Steve Zdonwick. It provides a program synthesizer called Myth for a much simpler ML-like language as opposed to our much more complicated Scheme, and it's extremely performant, but it has some constraints that make it not what we want. As an example, here's the custom language that the Myth program synthesizer uses. As you can see, we define nat as an inductive type, and we define list as an inductive type, not dissimilarly to the first step of the design recipe. Then, we specify that we want to make a function called stutter, which takes in a list and returns a list, that duplicates every element in the list. This is the synthesized implementation that Myth comes up with, which is fully correct and also follows a very similar structural decomposition template. Altogether, it seems like this is effectively what we want. So what's different in our beginning student language? First off, we have a lot of non-inductive data types that Myth's language cannot express, like symbols and strings and even images. In addition, Myth cannot guess constants. As in, if you had the function that merely evaluated to 5, it could not synthesize it. This is because the language that Myth uses does not actually have constants in the language, as we can merely express just s of s of s of s of z, for example. In the beginning student language, we also have various signatures that don't quite behave like types. For example, early in the class we introduce intervals, which represent closed and opened intervals of numbers, which aren't usually expressible in the standard type system. Finally, in beginning student we have a large collection of primitive functions, like plus, max, substring, string append, and so on. These aren't things that reasonably show up in the Myth language, as again, they only have inductive data. The core algorithm of Myth and also Bingus is to build this thing called a refinement tree. What we do is we take steps to refine a program. For example, starting with this length function, we could make a step that guesses a plus and then makes 2 new number holes. We could take a step that splits on the input, the list, and produces 2 new number holes. And we continue to do this, filling in holes as we go. Each node in this tree represents a partial program, and each edge represents some kind of hole-filling operation that we call a refinement. We can guess various different things, many of which would not be correct, but eventually our fully complete program will show up in this tree. So what are the edges of this graph corresponding to our refinements? We start off with introduce lambda, which is a very simple refinement that merely binds a variable if we have a hole in the shape of an x to a y. We bind a variable that is of type x and put it in the environment, and then we make a y-shaped hole. Guess var states that if we have a variable in the environment with the given shape, we can plug that hole with it. For example, if we had a number n in the environment and we had a number-shaped hole, we could put n in that hole. Guess const guesses a known constant. For numbers, this is 0 and 1, and for booleans, this is true and false, etc. Or one from a unit test. For example, if we had a test that says that depth of some tree is 3, we could guess every number inside of that tree as well as the number 3, because those all appear in our unit tests. Guess app, which says that given an x to a y and an x hole, we can create a y hole. So, for example, if we have a number-shaped hole, we can guess plus number, where the 2 numbers are 2 new holes to work with. Finally, we have guess template, the interesting one. Given an inductive type x in the environment, we can try the template for that signature and then extend the environment in each hole with any recursion. For example, if we had our depth function from earlier, in the node case we will extend the environment with the depth of node left and depth of node right. We now discuss our intents for the Bingus program synthesizer, how we intend to use it at IU, and what could possibly come in the future. First off, being the beginning students and the other student languages are pedagogical subsets of Racket, Bingus is largely designed for pedagogical use. In the 211 curriculum at Indiana, we have a lot of checker scripts that are designed to manually check our functions and were written by a crack team of undergraduates over the course of spring 2022. The problem is that these checker scripts can't reasonably guess everything without a much more complicated heuristic. For example, we have this test for land rockets in our checker script. Here, we have a function that, given a time, produces an image of a rocket landing. The problem is that because students can use various different sprites for the rocket, etc., we can't actually reasonably test this very well. Instead, we merely check that it produces an image for certain inputs, that it changes from time 50 to 150, and that it doesn't change from time 201 to 202. With Bingus, we can insert holes into the student code, and then have Bingus synthesize the rest. Because we have a fully deterministic algorithm, which is spread for search, this should be relatively easy to check against, and then we can reasonably say that the student code is correct or incorrect. In addition, we can use Bingus to determine inconsistent sets of unit tests. Let's say that a student writes a set of examples that no reasonable function exists for. In this case, Bingus would blow up. It would repeatedly create new refinements. It would continue to guess templates that it's already guessed. And despite the fact that the graph is infinite, it would take a very long time. If we put a time or a size cap on the graph that we produce, we can reasonably say that the tests that the student has written have no good function that will produce that, aside from just dispatching on the input. In this case, we can reasonably provide the student with feedback, saying, your tests are wrong, go see an instructor, or possibly try this or this. Finally, we can use Bingus to determine if a function follows a certain shape, or if the template that a student provides is correct. The canonical way to write a template is usually with cond, but you could imagine a version with and or if you're merely working with booleans. We can actually have Bingus fill in the holes in students' code, and in this case, we can actually determine if the template is correct by saying that the function must be at least this complicated or so, and that if you fill in these holes, you can guess the final program. The problem we currently face is that this synthesis algorithm is rather slow and naive. In particular, it takes about 2 to 4 seconds to synthesize a function like length or depth, as shown earlier. Despite the fact that the algorithm is very, very similar to the myth paper, and myth performs excellently, our problem largely lies in the large space of primitives that we have. In this case, one good idea is to use Dijkstra's algorithm over our tree instead of breadth first search. We could assign each function a weighting. For example, we could give plus a higher weight than max, because we're more likely to use plus and should guess it more often. We could also interleave the refinements we use. Rather than guessing all of the constants and all of the applications, we could merely guess the constants and applications interleaved, etc., etc. The only problem with this is that this destroys our invariant that we always produce the smallest possible program. One other idea is to remove unit tests from consideration inside of conditionals. For example, if we have an input L and we have a cond that ensures that L is a node, then we can reasonably exclude any test that says that L is a leaf. This means that we have less constants to guess as we go further and further down into our conditionals. Finally, Myth's version of our refinement tree approach is significantly simpler than ours because of the lack of primitives, and also it is cached, meaning that we can just fill in the holes in their trees, whereas we repeatedly add holes. Caching this would make it significantly simpler. Another thing of note is that since we have a lot of interesting data, like numbers and strings in our language, this algorithm doesn't particularly work well for those. For example, here's a function from a 211 problem set that takes the days since the 1st of January in year 0 and returns the year. The problem is that this doesn't actually follow any kind of structural template, and we don't have all of the constants that we need to create this function in our examples. So, what we can do instead is shell out to another program synthesizer, such as Rosette, which is much more performant at synthesizing code with strings and numbers, given that it's based off Z3, rather than a standard enumerative synthesis approach. This could be implemented as another refinement. Instead of having guess app, we could do guess Rosette, which merely calls that synthesizer and determines if it can figure out something for the partial program in our whole. Finally, because this is code intended to be used by students, we need to figure out how to make it good. We need some way to call Bingus, and we provide a basic API that can parse the comments from student files. Here we have a data definition and a signature and a comment, and we are able to successfully parse all of this and provide the proper inputs for it to create a program. We also have a very Spartan quick script for Dr. Racket that runs a synthesizer with just the press of a button. However, it has a lot of things that have much to be desired. For example, not having the right parentheses shape, using a gensim despite having a TON in the left, etc. But we are able to successfully get from the left to the right with little issue. Thank you very much.